Dear friends, let me first speak as a YouTuber and then I speak as a mathematical friend. I am worried to see my YouTube, what is called YouTube Studio, number of subscribers gone down last 28 days after the dictionary program. So I guess the program was ill-timed because of the whole situation in and around us. So maybe that was not the best time to put the program in. Nobody in such situations like to wish to have don't wish to really listen to serious mathematics. Um, but I really want those people who are genuinely interested to mathematics to listen, at least have a look at my uh, videos. The reason I request you to do that is to go through the video totally, because if the average view time is 2 minutes 3 minutes, you don't really catch what's the idea behind the video. Because mathematical stuff, see, I am not having editing and a team around me and a kind of studio with lot of things, and finally I get something out which is very jazzy. I am a teacher who teaches at the high undergraduate and postgraduate and the PhD level. And I want to interact with you directly, speaking to you about the subject from my heart. So that's more important to me than making the team up. Obviously, I didn't make a single paisa from the YouTube, so I will not have that amount of money to invest and make kind of, maybe in the future when I'll be retired, I can become a full time YouTuber. I do not know what would be the scenario of YouTube at that time, maybe after 8 years I retire. And I really do not have too much time to invest in the YouTube thing. What I really understand is that when I talk about something serious, I've seen the views of my videos. There are certain very serious class lectures which has been given in linear algebra, for example, in optimization, for example. But those are very less views, even calculus, compared to when you're talking, about general things, about your life and about how things should be and how. But sometimes you really have to, pull your buckle up your seat belt and do mathematics, because that's what we are supposed to do as mathematics people. So I had promised that there will be something called long reviews of books. The first book that I choose in the long review is Linear Algebra Done Right by Sheldon Adler. So what I have with me is the third edition of the book, and the fourth edition is already published. I choose this book because I am happy that this author had made it open access. Means you can download the book from his own website. I'll download the fourth edition, maybe within a day or two, and to see the changes. At least one edition I wanted to keep in print. I had the print one. So he has two books, and both of them he has, given free, which is a big thing. It's a very big contribution to mathematics education. A big shout out and a thanks to Sheldon Adler. It helps a lot of people who are not privileged enough to buy those books, students especially, to have an access to such a fabulous book. And the book is really beautifully written. This book is not for a first course. This book is for a second course. Okay. Means you have some idea of linear maps in the form of matrices, a bit more about matrices, and here the whole analysis is in terms of linear operators. So you have vector spaces and linear operators, linear mappings between them, and their properties and what can be done, how they're applied. Of course, these come, you have studied possibly eigenvalues of matrices and all those things, eigenvectors. But here they will talk about linear eigenvalue of linear operators. And when it comes to finite dimension, there are the linear operators are nothing but matrices. And many of you have heard the delightful lectures of Gilbert Strang. But still, once you have done that, this is a good book to have a look at. So This book has 9 chapters. So what we will do is we will do chapter by chapter review. So today we will do the first 2 chapters, 10 chapters. So he pushes determinants to at the end, at the last. Determinants, actually, when his first book came out, when he possibly the first edition, the it also had a subtitle like "Down with Determinants" or something like that. So he's not very, he seems to be very fond of pulling determinant into the central core idea of linear algebra, because matrix algebra seems to do that. While Gilbert Strang takes a more matrix theoretic view, he takes a more operatic theoretic view. So, but there is nothing to be afraid of. Here, what happens is that this tells you that if you go to the next level of mathematics, that is functional analysis, will you become comfortable enough? Because in functional analysis in infinite dimensional vector space, where mappings are between infinite dimensional vector spaces, there is nothing called matrix. You can't visualize them as matrices. So they are just operators. So you need to think of them as operators. So let me read out what are the chapters here. So chapter 1 is called vector space. Chapter 2, finite dimensional vector space. The first vector space doesn't mean that we are talking anything about dimensions. Chapter 3, it's called linear maps. Chapter 4 is polynomials. Chapter 5 is eigenvalues, eigenvectors, and invariant subspaces. Invariant subspaces are not usually done in a basic matrix algebra course. Operators on inner product spaces. Operators on complex vector spaces, means here the scalar comes from the complex number field. They are complex numbers. That is alpha x when you write. So alpha is a complex number. Operators on real vector spaces, 9. 10 is trace and determinant. So here the things are very well laid out. It's a very operator theoretic view. So reading this will make you very comfortable handling functional analysis. So our idea is that not to just speak a bit about the book and finish it off, to go chapter by chapter and to go slowly and tell what are the contents of each chapter. So today I can do, for example, 2 chapters, and there will be some bonus thing which I will show at the end. Then maybe within a day or two, maybe tomorrow we'll come up with a 3rd chapter, the linear operator, which is a big chapter. We really have to discuss step by step. If something is to be written, I can put it up here with the thing written. And like the ones I did in the very first videos. See, the one thing that I have been trying a lot in the last few days to see how to focus my mobile and put it near the board and all, whether the board writings are clearly seen. But what I realized that no, with the lights in my office, the board writings are not very clear always. So something has to be done on that issue. Maybe I'll take some help, technical help, and try to do something to write on boards. Okay, so let me do whatever I can do at this moment. So the first chapter is on vector spaces, and here he starts with a colored picture. The book has a lot of colored pictures. So you see a woman and you see a man. The man in question is René Descartes, whose Cartesian coordinates you are all familiar with from class 11, for those who did mathematics. So René Descartes, explaining his work to Queen Christina of Sweden, vector spaces are generalization of the description of a plane using 2 coordinates, as published by Descartes in 1637. So the geometrical vectors that you learn in 2 and 3 dimension, the generalization of those properties makes what is the modern notion of a vector space. So now those properties become rules or axioms. Those properties which are true in the case of geometrical vectors becomes an axiom here. So any kind of object which follows those rules with those 2 operations of plus and scalar multiplication becomes a vector space. So here he starts first with the notion of a field. So here he starts that we will be talking about 2 very special type of vector spaces. One is Rn and another is Cn. You can see the writing here. Rn and Cn. complex numbers and higher dimensional vectors, real numbers. So he doesn't make any statement whether these are vectors or not to be starting with, but he understands that many of you already have an idea that these are really vectors, right? So he does all these kind of operations on these sets Rn and Cn, and he gives a name to R and C. So R and C are fields. So fields are elements of fields are called scalars, and so you draw scalars either from R or from C. So in the whole discussion of in this book, the notion of the field is either R or C. There you can write a more general field also. There it is there in advanced, much more advanced mathematics, but you do not need it now for your purpose as a student. So this is for really a math major student or a physics student or an advanced engineering student, especially those engineering students who are going to do research in engineering. They could easily be using this book. So the initial part would look very simple. He talks about Fn, which is in a general, which means either Rn or Cn. So he essentially wants to show that the properties looks very much the same, right? So what is C of n? So any element, C stands for complex number. So any element Z which is in Cn consists of n tuples Z1, Z2 dot 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 Zn. So each Zi, Z1 or Z2 or Z3 or Z4 up to Zn belongs to the complex number field. It is the complex number, is a complex number C. It is in, and X is in Rn, x1, x2, xn. Each x1, x2 or x3, x4 they belong to the real number set. That you know very well. So you define what is a zero vector and all these kinds of things, which is almost like a geometrical vector. So you understand what I am trying to say. So if you read the book, and since I recommend everyone who is watching this video and who is interested in mathematics, please understand that linear algebra is the basis of modern mathematics. Without knowing linear algebra, you cannot do any valuable applications, which includes machine learning and deep learning. So modern day everybody wants to jump on that bandwagon of machine learning and deep learning. Please note that this is the basic subject. Without this, nothing will happen. So and you have to be very good at it. So I would recommend everybody to download Sheldon Adler's book, even the fourth one. So what I would do is, as I can fix up the board, is to do some exercises. You can see the exercises here. You can see the exercises. This side. These all exercises. Show that minus 1 plus root 3i by 2 is a cube root of 1, meaning cube root of this is 1. So because w cube x cube equal to 1, that polynomial equation has, if it has one real root, it will have one real root is 1, and the others two, it will have 3 roots by the fundamental theorem algebra, and it will have 2 complex roots which are in conjugate pairs. Okay, so so if there is one complex root of a cubic equation, there has to be another one. So there will be only one real root. In fact, complex numbers came because you wanted to solve cubic equation. You had no choice but to admit them. So that's the Cardano's story of Jerome Cardano. You have heard about the names of Cardano and Tatragali about regarding the cubic equation. Both were mathematical rivals. But Cardano also wrote the first book on the laws of chance. Some way the father of modern probability. So anyway, so maybe you should do all the exercises, and maybe I should choose one or two problems and then try to have a different session. Here is a section called section called definition of vector spaces. Here he actually defines a vector space. He defines what is the meaning of addition in a vector space. So addition on a set V is a function that assigns to an element u plus v to each pair of elements uv, which is in V, and that u plus v is also assumed to be in V. This is called the addition property. So whenever we take an addition property, we add what is called the closure property, that the sum must also be in the same set. The same is about scalar multiplication. You choose lambda from f. So f is either R or C. Then lambda of V, where V belongs to C, must also be an element of V. And then you have those properties of what are the properties the plus sign should have, and what is the property the scalar multiplication lambda into x should behave, and their combination should have. So you have the additive identity, which is 0, that is 0 plus any V should be V, and so on and so forth. So you already have an idea of many of these things. The first chapter is pretty simple. But it defines what about a set called F, capital F of infinity. You can see this, capital F of infinity. So each element now belongs to the X. Every element here is a sequence now. F infinity is a class of sequence. So every element of F infinity is x1, x2, x3, x4, x5, x6. It just goes on. It's a sequence, right? So how do you add such sequences? What is the meaning of scalar multiplication? That is all defined, and you should be able to prove that this is also a vector space. So the space of sequences, say real sequences or complex sequences, are vector spaces. Okay. So now there are a lot of properties which are additionally proved in page 14 and 15 of this book. For example, uniqueness of the additive identity. A vector space has a unique additive identity. See it here. The vector space here, just a moment. The vector space, look at this theorem. A vector space has a unique additive identity, right? So this kind of results are there in this chapter. So then it comes to subspaces. So you have a subset of the vector space. So you take some elements of the vector space, not all, but they will also form a vector space. When that happens, 0 must be there, and for any two elements A and B of that subset, A plus B must be in that subset, and lambda V must be in that subset if V is in the subset. So you basically, the subset itself is a vector space again, right? So here again there are examples and lot of information additionally in small boxes, and huge example. Then you talk about direct sum of subsets and subspaces. So U and V are two subspaces. Then U plus V is a direct sum if and only if U intersection V is just the 0 vector. For example, if you take the x-axis and the y-axis in R2. So these are subspaces in R2. R2 is a vector space itself. So subspace is x-axis and y-axis. So what is the direct sum of x-axis and y-axis? It is R2 itself, right? And you see the intersection between the x-axis and y-axis is just the 0 vector. So that is the idea of it. So then comes, of course, try out the exercises, which is pretty fun, some of these exercises. Chapter 2, he talks about finite dimensional vector spaces. These are vector spaces which dimensions are finite, like R2, R3, C2, C3. And for example, I am sitting in R3 at this moment, right? So, and you are also walking or observing this video by sitting in R3. So Paul Halmos, one of the greatest of all American mathematicians of the 20th century, was the first mathematician to write down the first modern book of linear algebra. So it's written, you see, American mathematician Paul Halmos, 1916 to 2006, who in 1942 published the first modern algebra book. The title of Halmos's book was in the name of the title of the chapter. So the name of the book was Finite Dimensional Vector Spaces. I had a very old copy which I again picked up from the College Street of Calcutta. Those who have never been to Calcutta, if you ever be, and is a math lover or a science lover, should definitely be to that amazing place called College Street. and you do not know what gems you can pick up at very low price. So in finite dimensional vector spaces, he starts with the notion of linear combination of a finite number of vectors. So linear combination is the key thing about linear algebra. And that is what Gilbert Strang also tells in his book, that linear algebra consists of two operations. One is addition of two vectors and scalar multiplication. By combining these two operations, you can build whole linear algebra. Everything, including matrix operations, just reduce to this. I wish I had an opportunity to actually give a talk on linear algebra and actually teach a full course on linear algebra. So, in fact, one can base it on this book. So, then you talk about a span of vectors. So, you have some finite number of vectors in a vector space. Now, span means you are having all possible linear combinations. So, linear combinations, if I say I have vectors v1, v2, vm. So, each with first what I'll write, what by linear combination I mean, I multiply each one of them by a scalar. So, a1 into v, then plus a1 into v1 plus a2 into v2 plus dot 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 an into vn. So, what is the meaning of this scalar multiplication? So, if you have a geometrical vector, say in R2, and lambda is from R, then lambda of R, lambda of a vector v, if lambda is greater than 1, means you are stretching the vector. And if lambda is less than 1, you are shrinking the vector. So, I had very long ago when I started the YouTube, I had initially spoken about vectors and I had given some these kind of descriptions. Okay. So here they talk about span of a finite set of vectors. So span means I will take the vector and have all possible linear combinations. So I'll take a1, a2, am from f. F could be R, could be C. So but in the beginning you have to fix either you take R or C. It cannot be that you some scalars you are taking from R, some scalars you are taking from C. The moment you do that, your vector space is a vector space over C. Means you have taken, because every real number is also a complex number with 0 into I. So imaginary part is 0. So which means that if you say real number is my field, then you have to multiply only with real numbers, no complex number comes. So once you multiply once with any complex, make a combination with complex numbers, you are taking your vector space over the field of complex numbers. So if you see some combinations with real numbers, some combination with complex numbers, that means the field is definitely a complex number. The field is the complex number. So here they talk about linear spanning. So if you have a span of a vectors, so it's finite number of vectors. So v1, v2, dot 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 vm is a set of vectors. And then you take all possible linear combinations. So one possible combination is a1, v1 plus a2, v2 plus an, vm. So this a1, a2, am is one set of real numbers, maybe real or complex, some from f, just from f. So here I am trying to become more abstract, more like the pure mathematician, that it is from f. So I take another set of vectors. I can take another set of vectors. There are many uncountably infinite possibilities, such possibilities. And so I get an collection, uncountably infinite collection. Say suppose f is my real number line. So there are uncountably infinite possibilities of a1, uncountably infinite possibilities of a2, and so on. So does the span of a finite number of vectors is countable? The answer is no, because you take a1 as a real number and make everything else is 0. So you will get the vector a1 v1. Now you can change, a1 can have uncountable possibilities. So this a1 v1 form itself is uncountable. So all other, if you take anything else added to it, it becomes uncountable. So you essentially have your span is an uncountable set of vectors. So what is the span of, say, the vector 1, 0 and 0, 1 in R2? In the vector, if you take the two-dimensional vector and with R as the field, then if you take alpha of 1, 0 plus beta of 0, 1, it simply means alpha beta, means the whole R. R2, and that is obviously you have infinite, uncountably infinite number of possibilities. So span has a very interesting property. So if you take a set of vectors v1, v2, vm, so when you make a span, you actually make a vector space out of it, because you can choose a1, a2, an, am all 0. So you can always bring 0 in there. So what you get is a subspace. So span is always a subspace, and this subspace is the smallest subspace containing these vectors v1, v2, vm. There could be other subspace also bigger than the span, but this is the smallest one, right? So that's pretty interesting. Of course, these needs a more board work to make you understand, but I am trying my best here. So a vector space is called finite dimensional if I find a finite list of vectors or a finite number of vectors which spans the whole vector space. Then I will call the vector space finite dimensional. If I cannot find a finite set of vectors whose span becomes the vector space itself, then it is not finite dimensional, right? Here there are a lot of good examples, and I would like you to have a look at this example, and I wish, of course I cannot say that you should, but I wish you just do that and you will be only rewarded. And if it is not finite dimensional, we call the vector space to be infinite dimensional. Here they talk about linear independence and linear dependence of finite set of vectors. So what happens is that a set of linearly independent vectors, finite number of vectors which are linearly independent and spans the vector space forms a basis. And if a basis has a certain number of vectors, every other basis which is a finite dimensional space will have the same number of vectors, and the number of vectors in the basis is then defined as the dimension. Of course, most of you know what is linear dependence and linear independence. So linear independence simply means that if I take a linear combination of a finite number of vectors, and then if the linear combination turns out to be 0, then all the scalars associated there has to be 0. All the scalars associated with the linear combination, that is a1, a2, am, they must be 0. And linear dependence means that this need not happen. There is at least one ai, could be a1, could be a3, could be anyway, at least one of them which is non-zero. So that's about linear dependence and linear independence. Suppose you come in two-dimensional vectors, geometric vectors. Suppose you take the positive x-axis as one, so 1, 0 as one vector and minus 1, 0 as another vector. So what is the relationship between them? So minus 1, 0 plus 1, 0 is 0, 0. So a1 is 1, a2 is 1, non-zero. But if you have 0, 1 and 1, 0, then a1 into 1, 0 plus a2 into 1, 0, that would give you a1 and a2, these vector a1, a2, that will be 0, right? And that means that a1 must be 0 and a2 must be 0. So linear independence in two dimensions simply means if either the two vectors are in the same line in the same direction or in opposite direction, then only they are linearly dependent. If your angle is not, between the vector is not 0 or not 180, then of course the vectors are linearly independent, right? So linearly independent vectors plays a key role in the study of linear algebra in finite dimensions. So that is why, because of that, all this idea of rank, column space, row space, and everything has come. The linear independence, the idea of linear independence is key to developing the simplex method in linear programming, for example. So I'll not take much of your time, but here is all results about linear uh, algebra. I mean, this about. Uh, so, for example, every subset of a finite dimensional vector space is finite dimensional. Then he talks about basis. So, a basis V is a list of vectors in V that is linearly independent and spans V. So, every basis, one of the major, every finite dimensional vector space has a basis. It's a very, very important result. Another is the extension theorem, which says that if you give me any independent set of vectors in a vector finite dimensional vector space, it can always be extended to a basis. So with these some very basic ideas, I will rather, so 2C talks, the 2C section here talks about dimensions. So it talks about any two bases of a finite dimensional vector space have the same length. That is, the number of elements of the basis is same. Right. So this is one of the key idea that gives rise to the notion of the dimension of the space. And then of course there are several other theorem, the rank nullity theorem type things, and these are important, which you will soon, when you learned about rank nullity theorem about linear maps very soon. So this is about, for example, if u1 and u2 are finite dimensional vector spaces, then dimension of u1 plus u2, that is addition of the two vector spaces. Addition of two vector spaces means is not union. So you take a vector x from u1, take a vector y from u2, and add these two vectors in the vector using the vector addition, and that will be a new element which will be in u1 plus u2. So dimension of u1 and u2 is equal to dimension of u1 plus dimension of u2 minus dimension of u1 intersection u2. So these kind of formulas where possibly u1 and u2 could be events, and plus could be replaced by union, and dimension could be replaced by probability. You have these kind of formulas all over in mathematics, and so there is a kind of hidden unit, you might think. Maybe so, I cannot tell at this moment, but here the proofs are done in a very, very beautiful way. And I wish I get a chance someday to teach a course based on this book, which is very difficult, I would say, unless I teach online on my own. But that needs a kind of board and all kind of thing. I am trying to see if I could possibly do this through, actually have my what is that called, iPad connected to this one, and then try to open the notebook and see what I have written, and I write step by step slowly and see if I can do these things. So maybe these are all dreams, a part of the whole program, and I hope I've taken too much of your time. Actually 33 minutes on a weekend is not good. So maybe day after tomorrow we will start with linear maps, and here you see Gauss looking at you, the prince of mathematicians. Those who do not know, the possibility the last written absolutely different linear algebra book is from Gilbert Strang. So those who have not seen the full video would miss this, the linear algebra for everyone by Gilbert Strang, and I am very, very proud to say that this is a signed copy by Gilbert Strang, and I am delighted. Gilbert Strang is a legend of linear algebra. I think no one in the world can teach or talk about linear algebra better than him. So with this little fact and this little showing you this book, I say a goodbye to you, and I wish you a happy evening. And those who love mathematics, concentrate on mathematics. That will give you real happiness. I know there will be somebody trolling me that you cannot find happiness in mathematics. That is not the way you find happiness. There are other better ways of finding happiness. I have tried several ones. I didn't find them. If somebody asks me this question, my answer is I have not found happiness in other methods. I have found great happiness in doing mathematics. It's really fun because knowing mathematics would allow you to understand what is true about this world. For example, I show you at the end this book, General Relativity for the Gifted Amateur. This is by Tom Lancaster and Stephen Bundle from England. I think they're from Warwick, if I am not wrong. Yes. So this book, it's largely about geometry. It's about differential geometry, and it's about linear algebra. Once you have a good idea about linear algebra, you will be able to understand tensor calculus. And this is a very, very big fun book. It's published this year, and I hope I'll be able to do some special sessions on as a part of our geometry celebration on general relativity, because geometry is very deeply linked with it. So there are several other books which I would like to say before I go. Not like to say, but just show one book. Is Elementary Differential Geometry by Andrew Presley. So this will also come under the long reviews. So thank you for being so patient. And as I have told you, those who are really interested, please go through these videos. You will ultimately end up benefiting. I hope so. And I hope I could be of some help to you. Thank you so much, and all the best for the evening.